Hey there, folks. It is September 21st. So we're almost, uh, it's almost fall. The summer is just got a few more hours left. So we are looking at the third of our three different types of rocks today. We're looking at metamorphism. We've looked at igneous rocks and we've looked at sedimentary rocks, and now we're going to look at metamorphic rocks. So let me warn you. So metamorphic rocks can be rather complicated. So I'm going to try to make this as simple as I can and let you see the very basic stuff. But when you start reading your text, you're going to get into all kinds of big words and all kinds of big ideas about how metamorphic rocks are formed. And but I want to remind you that it's really a lot simpler than that. And I don't expect you to know all the chemical processes and all that sort of thing about metamorphic rock formation. So it's real important that you watch this video so you kind of get the basics. All right, so we're going to jump right into it. Well, I've got a few metamorphic rocks I am going to show you. Again, like sort of like sedimentary rocks, they're kind of boring because you either have to see them on a big scale, like looking at the side of a mountain that's undergone metamorphism. That's kind of cool. Or on a very, very small scale, like through a microscope, where you can actually look at individual grains and see metamorphism. So just looking at the rocks themselves, they look kind of boring. But I will show you a couple. The first one I want to show you is one you've seen before, of course. This is quartz. And we said when we were looking at minerals, quartz kind of looks like glass. So what would happen if we took some quartz and metamorphized it, in other words, added some heat or some pressure, and we would get quartzite. So here's the exact same rock, one of them as a mineral, and the other one as a rock that has undergone metamorphism. The other one I'm going to show you is slate. Slate is a sedimentary rock. And again, you've probably heard of slate. We use it for roofs. We use it for pool tables. We use it for chalkboards. We've got some chalkboards there at Simmons that are big, heavy chalkboards because they're actually made of slate. And they make good pool tables and chalkboards because they are cut right along this line. In other words, the foliations, and we'll talk about that more when we get into the chapter, are so compressed and so perfectly flat that I can chip it off to the point where I get a perfectly flat surface. And again, that's why we would use it for something you could write on. So again, metamorphic rocks aren't very pretty to look at, but they are kind of neat when you look at them, like I said, in a mountain range or in a microscope or something. So let's jump into this chapter. This is chapter 8. And again, this will be the last of our three different types of rocks. Now, as we know, the basics of metamorphism is that your book talks about the word itself here. So meta means essentially to change, and morph is shape. We think of metamorphism like with butterflies, right? Butterflies start out as caterpillars. That's their immature condition. And they will metamorphize or change into a butterfly, their sexual or adult form. Other organisms like us, we go through what we call incomplete metamorphism, don't we? And you all did it back when you were about 12 years old, 11 or 12 years old. Your voice started changing and you started growing hair in places you didn't have hair before. So that is a kind of metamorphism. But in rocks, we're talking about non-living things. So we're talking about things that happen to rocks in the environment. So these are very basic things. And we know that metamorphism happens through heat or pressure, or a combination of the two. So how can temperature change a rock? Well, you can imagine igneous rocks change quite a bit, don't they? They literally completely melt into a liquid form and then refreeze into a new kind of rock. And we've seen that within that freezing and change in phase of the rock, we get crystal growth. And so based on how fast or how slow it heats up, or freezes, we get different kinds of rock. Same thing can happen here in metamorphism, where we don't actually melt the rock, do we? We just sort of add heat to it so the rock becomes more plastic. And again, I'm using the word plastic as a verb, not as a noun. It's not something that you would buy that's made of plastic, but rather plastic in that it was rigid and it becomes flexible. I like to think of it in terms of my chocolate cookies that I buy at the store and then leave them in my car when it gets really hot, right? They started out as nice, firm chocolate cookies that I could just take out and eat. And then by the time I get back in the car and it's warmed up, they are definitely not very firm. They haven't melted completely, have they? They haven't completely turned into liquid, but they definitely have lost their shape, and they're definitely a lot more gooey to eat. So that's kind of what we're talking about in terms of the heat process. In terms of pressure, as we know from our physics classes, right, that as we add pressure, temperature can go up. So really just adding pressure can change temperature, but pressure itself can change the shape of rock, can change the shape of the crystals inside of the rock, and we'll see that in a little bit more detail later. Again, your book throws a lot of big words at you here. You'll see the word protolith. Protolith. Remember, proto simply means first, and lith means rock. So when we talk about a metamorphic rock, and we talk about its protolith, we're talking about what the rock was before. So in terms of my quartzite, the protolith would have been the quartz that was nice and clear and looked like a piece of glass, right? So this is a very interesting little story here about a guy by the name of James Hutton. He was kind of literally the father of geology, really a fascinating guy, and some of the stuff he came up with. So that's kind of a neat little story to read about, the fact that he sort of discovered metamorphic rocks and figured out what they were. So your book starts talking about what these are, and we're going to look at two general kinds of rocks, and I've already showed them to you, metamorphic rocks. We're going to look at foliated and non-foliated rocks. So the shale, or excuse me, the slate that I showed you, which is the metamorphic form of shale, would be a foliated rock. In other words, it was probably at one time a sedimentary rock. And so within those sediments kind of get squished, but we can still see where those layers may have been. So that's what we talk about when we talk about a foliated rock. Non-foliated rocks would be more like the quartz, where we have crystallization, and that crystallization is kind of in a 3D pattern, and there we can see changes happening within the crystals themselves. So those are the two basic ideas that we're talking about here, and your book goes into a little bit more detail, talking about recrystallization, phase change, metamorphic reaction, all these sorts of things. Having to do with what happens to the crystals themselves. Remember, when these minerals form within rocks, they are crystallizing, and because of they are hot and they are cooling down, now we have a rock that is cooled down, but it's kind of being reheated, so it sort of regenerates that crystallization. That crystallization can kind of start again. And the interesting thing is, in some metamorphic rocks, they can actually start exchanging molecules. So within this recrystallization, we can get actually new molecules that can change the rock at a molecular level, not just at a physical level. And again, here's a look at some shale that's being turned into something called gneiss. We don't pronounce the G. And then a piece of limestone here, which is going to be turned into the metamorphic form of limestone, which is marble. And we'll see that in a little bit more detail later. So your book starts talking about changes due to heating, and we already talked a little bit about that, to where as the rock heats up, the crystallization can change. Um, Here at the bottom, you can see a piece of quartz, or excuse me, you can see a piece of granite that's going to be rechanged and formed into a metamorphic form um, of granite there on the right. So this heat actually can affect the crystals themselves. And so that's why I said these rocks would be interesting if we could look at them through a microscope, because we could see this recrystallization, this reformation. Here you can see two different rocks, the protolith, the first rock, which was probably a sedimentary rock because we have fossils, right? And then the metamorphic form of that, where the fossils now are gone, right? But the chemicals inside the fossils have sort of been rearranged, haven't they? And crystals have allowed to be regrown. And so we see, again, a piece of limestone that starts out as something where, like I said, in a piece of limestone, we could look and actually find fossils, couldn't we? But if it got reformed into the metamorphic form, which is marble, if you look through marble, you couldn't find any fossils, because all those fossils then have been reformed. They're the calcium and the calcite within the fossils themselves that the little animal made his little shell out of. All that chemical has kind of been reformed into something new, a new crystal, and the fossil itself now is gone. Pressure, of course, can happen in lots of different ways. Mostly, rock is heavy. So if you've got rocks that get piled on top of rocks, which get piled on top of rocks, which get piled on top of rocks, building mountains, you can imagine that the rocks at the bottom are going to be subject to a great deal of pressure. And so you would probably find metamorphic rocks at the bottom of a mountain rather than at the top. Now, if you've ever been to Grand Canyon, you see this at Grand Canyon. You look out on the canyon and you see all these beautiful sedimentary rocks. You can see all the beautiful layers and the different colors. But then if you were to go down in the canyon and go through it on a raft, right, or hike down to the bottom of the canyon, when you got to the bottom, you would see some very different kinds of rocks. You'd see rocks that are twisted, rocks that are, you don't see those delineations as clearly. And so you're looking at some very significant metamorphic rocks. So I have a little question for you, and then I'm going to get to the answer at the end of the chapter. All right. So here's kind of my question. Here's kind of my puzzle, as you might imagine. So I travel to Tennessee occasionally because I've got some family down there. And as I'm going to Tennessee, I'm going down 75 south to Knoxville. And as I go over the mountain, if you've ever taken that trip, you have to go over, if you're staying on the interstate, you have to go over Pine Mountain. And as you do, and you get to the top of that Pine Mountain, you drive through there for a few miles, and then you go back down towards Knoxville. But as you're driving through there, you'll see some rock cuts. And the amazing thing is, all those rock cuts on top of the mountain, on top of Pine Mountain, all those rock cuts are metamorphic rocks. So my question to you is, if pressure and temperature change rock into metamorphic rock, and I should find rocks at the bottom of the mountain, why, when I go over Pine Mountain, do I see metamorphic rocks at the top of the mountain? So that's your question. Think about it, and we will answer it at the end of the chapter. So let's keep going here. So can rocks change through temperature and, oops, sorry, I do that every time, sorry. Can rocks change, I gotta go get back to my chapter here, sorry. Can rocks change from pressure and temperature? And the answer, of course, is yes. We've already kind of looked at that. That as you increase pressure, you can, in fact, increase temperature at the same time. Or you can increase the temperature and pressure at the same time, like with, say, rocks that are buried. And then suddenly, so there's a lot of pressure on them already. And then suddenly you get a pluton of molten material coming up from somewhere. Possibly could form a volcano, maybe doesn't form a volcano, but adds a great deal of heat inside the earth. at that particular point, then you can definitely get some very interesting metamorphic rocks at that point. All right, so here I told you it's going to start getting kind of deep, and I really don't want to get too deep. We're going to talk about compression and shear and preferred orientation and all that sort of thing in the book. I don't need you to understand that completely. You definitely need to read it and muddle through it, as it were. But and please use the pictures; they'll help you quite a bit, especially when we talk about the different types of grains and the way the kind of the very small portions of this, where you need a microscope to actually see what's going on in some of these rocks. But this is just kind of going into more detail in terms of pressure, and we're not going to spend a huge amount of time on that. But again, it is very interesting. Now, these pictures are kind of telling too, because it kind of shows you what these forces look like and how those forces can change the shape of rock. We kind of think of rocks as being very strong and hard, and you can't really, if I took a rock and I stomped on it, I'm certainly not going to be able to make a metamorphic rock, am I? But you can imagine that there are forces in the earth much stronger than me stomping on a rock, and so these rocks can and are formed. There you can see a picture like a house of cards where the cards are built up, and they're all kind of in that lattice formation we think of as crystals, kind of a three-dimensional form, and then with someone splatting on those, stomping on those cards, you can definitely change their shape, can't you? And that's what we see in some of these crystals, where the crystals began as kind of a three-dimensional crystal, and then they kind of get squashed. And we can see that very clearly in certain kinds of rocks. We're going to look at some foliations here. So foliations are, again, most of the time happen with sedimentary rocks that have become metamorphized, because then the foliations themselves sort of get metamorphized, but they stay in the rock. And so you'll see this a lot of times if you look at a mountain, and you saw that at the very beginning of the book. You saw the picture of a mountain, and you saw the rock in the mountain, and you saw how at one time all those layers were probably nice and flat and straight, but now they're all twisted and bent and curved, and that would be a big clue that you're getting some metamorphic action happening. So different types, we've already looked at a few. There it talks about slate, the metamorphic form of mudstone or shale. And again, it's a foliated metamorphic rock. There are other kinds of again, foliated metamorphic rocks like limestones and sandstones that can also be changed into metamorphic rocks. Here you see schist. Starts out as a phyllite, which is a fine grained metamorphic rock. Caused by mica. It's got some mica in it. It's kind of a shiny material. And then add more pressure, more temperature, you get a schist. And then finally you get gneiss, which is a rock where you can actually see the different colored layers. And those layers now are crystals, but at one time were sediments. And so let's see if they're going to show us a piece of gneiss. We'll look down here and see. But anyway, here's a gentleman working on some slate. Again, the foliations are so tightly packed and so straight and smooth that you can literally take a piece of slate, and if you follow the grain, you can break it into little slabs of rock and use them on your roof. And so a lot of people, the earliest shingles were made of rock, were made of slate. There's a gentleman taking a rock and turning it into slate. And you may have seen some houses around. There's a few houses here around Louisville that have slate shingles. And then here we're looking at different types of foliations. For example, here's one that's fairly straight. And then here you can see the one that's probably been subjected. This has probably been mostly pressure. This is one that's probably been a combination of pressure and temperature, where the rock is literally starting to melt, starting to become very plastic. And so the foliations become very, not very straight. Anyway, let's keep going here. So again, these rocks are kind of neat when you can see them exposed as bedrock and see the different layers. Here you can see some rock that has been metamorphized, where you've got different kinds of rock that have literally been pressed together into one rock. So it's kind of a conglomerate sort of rock where rocks have literally been not exactly melted, but they've literally been fused together into a larger type of rock. They talk about here intensities, and again, we're not going to get into a whole lot of this, but you can imagine that some rocks that have a little bit of pressure, a little bit of temperature are going to change one way. The rocks that are under higher pressure, higher temperatures are going to change probably in a much greater fashion. So a lot of times with metamorphic rocks, if we know what we're looking for, and we know what the rock, the protolith was, the beginning rock was of that particular metamorphic rock, we can kind of judge how much pressure has been applied or how much temperature that rock has undergone, right? Here's an example of some marble. This is some marble in Italy, I believe, where Michelangelo used to get his marble. It's probably the marble that was used to make the famous David, probably came out of this quarry. But this is rock that's undergone quite a good bit of pressure and temperature, and so the marble was very hard and very there weren't a lot of weak spots in it. Let's put it that way. And so you could carve something like statues and things from this kind of marble. And so it's very famous marble in Italy, caused by this kind of heat and pressure. And so again, here the book goes into a little bit more detail than we need to worry too much about, but it is very interesting to look at and see if you can see some sort of pattern to what they're talking about, and be aware of that. And again, this is an interesting little tidbit here, but I'm not going to go into a lot of detail with that. But it is interesting to see where some of these zones of metamorphism are. As you can see, there's quite a few of them up in the Northeast, where we have the Adirondack Mountains, and so you'll see a lot of these metamorphic rocks in mountains. Again, because we know of tectonic activity where mountains are subjected to the plates themselves are subjected to a great deal of force, right? And here you can see that in detail here, where they're talking about a young mountain range being pushed together, and as the temperature, as this rises up, the temperature increases as the pressure increases, and so you can get a lot of metamorphism here. But here we have an active rift where the plates are coming apart, aren't they? And as the plates are coming apart, there's not as much pressure, but we have a lot more temperature. So we can see metamorphic rocks in both areas, can't we? Where we have a lot of pressure, which can create temperature, and places where we don't have a lot of pressure, but the fact that the rocks are coming apart and we're getting this molten material coming up from the mantle, from the mantle, that we can see these metamorphic rocks in these areas as well. So the different types of metamorphism, we talked about thermal or contact, so that's what we were just discussing about heat coming up from the middle of the earth causing metamorphism. Burial metamorphism, that's what we were talking about in terms of mountain building, where sediment gets piled on top of sediment, gets piled on top of sediment, and the weight just literally is so much pressure that you can create metamorphic rocks that way. Dynamic metamorphism, where we actually get plates moving. Remember, we have plates grinding and running into each other, and these can cause a great deal of pressure and even heat, as we've seen with plate boundaries, getting lots of volcanoes and lots of that magma and that molten material coming up. You're not actually melting the rock, remember, it's just rock that's near that heat, right? The rock just simply becomes more plastic, becomes soft, and changes can happen, can cause metamorphic rocks to happen. Now, if you get in the heat, right, if you get melted, you're not a metamorphic rock now, are you? Now you can become an igneous rock. So there's kind of a fine line, isn't there, between whether or not you've actually melted and become an igneous rock, or whether you've just sort of become plastic and are a metamorphic rock. And a lot of that's got to do with, is there any of the protolith left? In other words, in igneous rock, the protolith is gone. I mean, it's completely melted and distributed, and it's gone. But if I can still see part of the protolith, if I can kind of figure out what the rock was before, then I have a metamorphic rock and not an igneous rock, if that makes sense. Again, a little bit more detail. They talk a little bit here about what, to try to think about what an igneous rock is, or excuse me, what a metamorphic rock is. We can kind of think of bricks. Bricks start out as mud, don't they? Back a long time ago, bricks are one of the very first building materials. And so what you would do is you would take mud or clay. You'd try to get as much clay as you can. And clay is basically mud, right? But there's not as much organic material. It's mostly rock, and the grain is very, very fine. In other words, it's not sand. The grain is almost like, much, much finer than sand would make clay. That's why clay feels so heavy. So you take that clay and you'd form it into a brick, and the first thing you would do is let it dry. So you would dry the bricks out in the sun, and people use those for a long, long time, sun-dried brick. Of course, the problem with sun-dried brick was that if it started raining again, the sun-dried brick would not be dry anymore. It would start getting wet and turn back into mud. Then people realized that what you could do is you could fire the brick. In other words, you could take this brick, this sun-dried brick, and if you got it very, very hot, right, you could literally melt the crystal. They didn't know what they were doing, but you could literally melt the crystals inside and fire the brick, and it would become hard so that even if it got wet again, it wouldn't dissolve. And so that's where we get brick. So to make a brick today, right, or any of the bricks that we think of as that we would build with here, you would take a clay brick, sun dry it, and then fire it, get it really, really hot, like a piece of pottery, and it would change, right? It would metamorphize. Crystals would change, and so now instead of individual crystals that could dissolve when it rained, now the crystals are locked together. They've sort of melted and fused and locked together into a brick that we could use, and it doesn't, like I said, disappear when it rains. This last part talks a little bit about the mid-ocean ridge and metamorphism we see there. Also, metamorphism we see around these subduction zones. Remember, areas where plates will dive under other plates. And then we talk about shock metamorphism. So shock metamorphism is places where there may have been a meteor hit the Earth. And the force and the impact of that meteor, that incredible instantaneous explosion of energy, can cause all kinds of really cool metamorphic rocks to form. Here's that really cool map at the end of all the chapters, nice and big, lots of information. Make sure you have that in your notes. Here's a really great way of seeing how things change from a shale, which is a low grade, or a sedimentary rock, how slowly as you increase the pressure and temperature, you get different kinds of rocks until finally you might get it so hot that it would melt, it would become an igneous rock. So here we would see the whole rock cycle right here, right? We start out with a sedimentary rock, add heat and pressure, it would change into a metamorphic rock, add more heat and pressure to the point that it melts completely, and now I have a new, and then after it freezes again, I'd have a new igneous rock. So there's the rock cycle in one fell swoop. Okay? Good question. Where do you find metamorphic rocks? So we're almost at the end of my chapter here. So let's ask the question again. Why did I see metamorphic rocks on top of Pine Mountain? Well, if you guess that at one time Pine Mountain was much, 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 much bigger, so that those metamorphic rocks that are now on top used to be at the bottom, then you're absolutely right. Pine Mountain and the Appalachian Mountains are very old mountains, so most of the material has been eroded away after hundreds of millions of years. But when it was formed hundreds of millions of years ago, it was huge. It was much, much bigger than it is today. And so those metamorphic rocks I'm looking at as I drive over the mountain today, we're actually at the bottom of probably miles of rock. And so that pressure created them literally hundreds of millions of years ago. And now today, of course, everything's eroded away, except now they're on top, aren't they? And there's probably even more metamorphic rocks below those. So that's the end of metamorphic rocks. Here are your review questions that you could use if you would like. And I hope everyone has a good day. I'll see you next time.